This is new to me, or I'm new to BuildSys. I wanted to start introducing the vision of my group at USC. And I lead this group called Innovation in Integrated Informatics Lab. We call it in short iLab. What we focus on is human building interactions with a specific focus on occupant-centered, behavior-driven built environments. We focus on how to make built environments adaptive and responsive. And there are various projects that we focus on. One thing that I have to emphasize is our focus is on the users. So we look into occupancy patterns, and obviously this paper is very much related to occupancy. We look into thermal preferences of people and try to model those preferences, as well as understand how those preferences could be implemented in buildings. We look also into visual preferences, which is a new area for us. And we also look at use patterns and preferences, like how habits actually trigger some of the energy-related behavior. For example, we try to see if people know that they're going to be absent for 30 minutes from their rooms. Does that trigger turning off lights events or not, or based on the luminous levels in the room, if that triggers change of lighting settings and such. One thing that I have to mention that energy efficiency is, yes, our focus, like many of you are also focusing, but something that I'm really interested in is not only impact of energy efficiency, but also users. So in my work, I have two objectives, making users comfortable and coming up with solutions that are convenient, and also reduce energy consumption. And this is at the core of it because I really believe in personalization of spaces instead of standardization. So I won't talk about thermal comfort, but when I say that people are comfortable in my building, what I mean is I'm able to provide them their specific individual preferences. And we do lastly try to focus on control. So given all these complex relationships in a building, different occupancy patterns, different preferences for thermal comfort, visual comfort, and different designs of buildings, how do we make use of this information, again, to increase comfort and reduce energy consumption? Having said that, the presentation focuses on occupancy. And this is a depressing fact that you all know. People spend, at least this is Americans, 90% of their time in buildings. So occupancy is important to us. We define occupancy as time sequence occupancy changes to represent how occupants occupy the space. And there are multiple applications, from building energy management to facility management to security monitoring to emergency evacuations and such. And we care about occupancy from a civil engineering architecture point of view, also to understand how spaces are utilized. So that's an added application area. So in my lab, we look at occupancy in two ways, real-time occupancy and long-term occupancy. Real-time occupancy is the occupancy status at each time point. Long-term occupancy, we call it occupancy profiles, which are the probabilities for classes of occupancy as a function of time. In this presentation, I'm going to talk about ambient sensing-based occupancy modeling, and we use ambient sensors because they're frequently used in today's buildings. They're also non-intrusive in nature. They have wireless communication abilities, low power requirements, and you have flexibility in terms of choice. So, and the presentation and the paper focuses on both presence, which is the binary occupancy, occupied, unoccupied, as well as real-time occupancy. Our hypothesis is occupancy regularly influences and interference with the ambient environment. Occupancy status and ambient factors can be mathematically or statistically bridged. So we're trying to find out how to make that bridge. So a specific problem that we're looking into is how do we globally model occupancy? And what I mean by occupancy is different classes of occupancy. So I'm really interested in training a model in one space and applying it in different spaces to be able to tell you at a given time step, how many occupants occupy in that space. From what I know, and you can correct me if I'm wrong, most of the occupancy work has been done locally. So you basically collect information from a space and train your model based on that you train the model for each space. However, this is quite costly, time-consuming, intrusive, and in most cases, it's really unrealistic to have the ground truth for each space. And what I mean by space is each room in a building. So what we proposed here is a cross-space occupancy modeling, and I'm not claiming that this modeling works for all kinds of spaces, but I am claiming that it works for geometrically similar spaces, and the way that we define it is two spaces are similar if they're within 20% of the area, if they have similar controls, windows and doors and such. So again, our objective is to study, to generalize the relationships between occupancy and contextual information, especially the ambient factors, and I'm going to take you through our approach from hardware to data collection to feature selection to supervised learning to performance. So contextual information is important to define. So what I mean by that is ambient factors, time and model occupancy at the time of a previous step. So to investigate this problem, what we have done is we have collected data from 6 rooms in 2 buildings at USC campus. So 2 of these rooms were in one building, 4 of the rooms were in another building. As you can see, those are 2 different buildings across the campus. And we purposefully chose these buildings to have different orientations. We also looked into we also wanted to have occupants with different job titles. So 2 of them are occupied by staff members, 4 of them by professors, and they had different schedules. So we collected data for each room at least for 8 months, from 2012 to 2014. And we tried to make sure that we have covered all 3 semesters, spring, fall, and summer, as well as all seasons in Los Angeles. So these are the data points that we have collected. We built these sensor boxes. This was part of a DOE project that I was part of. And we put all of these sensors, light sensor, acoustic sensor, motion sensor, carbon dioxide, temperature, relative humidity, PIR sensor, and door switch sensor. And we placed them about 1.5 meters from each door. And for the ground truth, we used a webcam which collected occupancy data every 10 minutes, and then we manually labeled, by looking at the images, the ground truth. So we have done a fair amount of work in this area, and these are the features that we have been using. We have categorized them into 3 different areas. Instant features, instant output of a sensor, like lighting level or binary motion. Count features are the number of times the sensor's output changes in the last minute, or average features like average value of a sensor's output for a certain period of time. For example, acoustic average for 5 seconds. But we realized that we have tested different methods and we weren't very successful. So we have gone through a feature selection process where we used our previous knowledge, where we took out PIR sensors, motion sensors, and acoustic sensors because they had low contributions, low information gain ratios to the modeling results. We included time of the day, class of occupancy at a previous time step into our feature list. Then we had missing values due to different reasons, electricity outages in the building, or sensors not working, or wireless communication issues. So we used K nearest neighbor to impute the missing values. And since some of the ambient factors are continuous and dynamic, their trends and variations during a certain period are more important than what's happening in absolute sense values at a specific time points. So we segmented the sequence of values for continuous ambient factors by a 10-minute window. And then we extracted statistics and included those into our feature list as well. So you all know too many features could cause overfitting. So we removed redundant features and we looked into information gain. And then we realized that 15, I think I'm going to talk about that, but so we have done some exploratory studies to decide on the final list. So these are the types and the sources of different features that we have used. We've done a preliminary analysis, and we realized that the number of, if you increase the number of features, your training model gets better, but then your testing, there's overfitting issue. So we looked into how many features we need, and we have decided we have 15 would be the maximum amount to train the model to avoid overfitting. And so these are the most influential features, 8 of the features based on the information gain ratio. So here is the PCA. So you can see that there are clear boundaries in terms of occupancy statuses. So there were 4 occupancy statuses in these spaces. Nobody is in the room, 1, 2, or 3 occupants. We have concluded that we can use a model trained from one room to estimate occupancy classes in another room. So for our method, first we implemented bootstrapping. So the basic idea was to resample of training data with replacement and reconducting the supervised learning on the resampled data. And we have implemented 5 supervised learning algorithms. And then since we had 4 classes and 5 methods, we have used ensembling method. So we use voting of the 5 classifiers. To be able to evaluate the performance, we calculated daily model occupancies and compared them with the actual occupancies from only 6 a.m. to 9 p.m. and only weekdays. And we have calculated different metrics, so the F measure, and then we calculated the daily RMSE, and we compared those two. So not only to investigate not only how many times the model could generate correct occupancy outcomes, but how far the outcomes deviate from actual occupancy if being modeled incorrectly. And then we looked into occupied, unoccupied detection accuracy and compare it to the number estimation accuracy to investigate whether binary occupancy detection and multi-level number estimation were correlated. So here are some of our results. So we used one room for training and then tested the model on the remaining 5 rooms. And the results are varying. Here you can see that, for example, in room F, all the F measures are above 0.8. In room C, all the F measures are below 0.8. So one possible reason could be that the ambient sensors in different rooms were calibrated differently, and they might have different accuracies, hysteresis, and dynamic characteristics, and some other uncertainties. Another finding that interchanging the room for training and the room for testing generated different results. And we assume we made our explanation for that is the same, that there might be different, it could be sensor related, or it could be particular occupancy profiles in a particular space. However, there wasn't significant differences between the 2 buildings, and so you see the daily F measures are between the 0.7, 0.9, with a mean of 0.8, and daily RMSEs range from 0.4 to 1.7, with a mean of 1.23. And the magnitude of the modeling deviations decreased as the overall modeling performance increased. So then we looked into detection and estimation, again to investigate the relationship correlation between binary occupancy detection and multi-level number estimation. And obviously binary occupancy detection performed better than the multi-level occupancy estimation, and they were logarithmically related. As the binary detection accuracy increased, the increased rate of number estimation accuracy decreased, indicating that some samples had irregular contextual information and cannot be correctly classified into exact occupied classes. So then what we have done is we have looked at different parameters in terms of performance evaluation. And those we try to understand. We dug into the data and tried to understand why we're getting the results that we're getting. We looked into level of real-time occupancy variations, degree of long-term occupancy difference between rooms, and we also looked at indoor and outdoor temperature differences and how those impact the results. So this is the real-time occupancy variation, and the definition of that is the ratio of occupancy class transition times for a day and average occupancy class transition times for the data collection period. And so occupancy variation level varied between 0.5 to 1.6, but the majority was between 0.9 and 1.2. And those two were the daily occupancy variation and daily modeling accuracy were negatively related. So they had a logarithmic relationship. This could be because of some features vary instantly with occupancy, and the model can still capture certain contextual changes by occupancy. Then we looked at the long-term occupancy distance. And these are the deviations of daily occupancy from occupancy patterns of different rooms. And the way that we calculated that was the Euclidean distance between actual daily occupancy of the tested space and occupancy profile of the trained space. There was a slightly negative trend, and the larger the deviation is, the less possible that the trained model covers the information necessary to model the tested samples. And the next one is, as I mentioned, the third one, I'm running out of time here, I think, indoor-outdoor temperature differences. Because we have been collecting this ambient information when the HVAC system was running in two different buildings, we wanted to understand what's the impact of HVAC on the ambient contextual information, therefore the occupancy. So what we've done is we average indoor-outdoor temperature on an hourly basis, hourly temperature on a daily basis. And for outdoor temperature, we use a weather station. For indoor temperature, we use temperature sensors. And here you can see when the indoor temperature is close to the outdoor temperature, around here, the daily modeling accuracies were high. And this is because there wasn't much interference of active conditioning on the ambient factors. When there was 3 to 5 Kelvin difference between indoor and outdoor temperature, the results dropped significantly because this is when the HVAC system kicked in. And then when there are large temperature differences, the decrease rate of modeling accuracy slowed down. Because no matter which room was used for training, the training data contained samples from the HVAC was on, and the HVAC system around larger differences worked continuously, so it didn't have that much of an effect. So with the last minute I have, so the results are promising. We only focus possibly on the occupied times between 9 to 6 a.m. to 9 p.m. So if we looked at 24-hour period, probably we would get better results. There are some limitations, however. We haven't looked at the quantitative contributions of each feature on the key metrics. And there could be more advanced feature construction methods that we would like to use. And there are other factors also, for example, orientation, space-related factors that that we would like to consider. And we have done this for 8 months, but only for 2 buildings, so longer period of occupancy data, like all of our research, I think, can use longer periods of data and larger range of buildings to generalize the results. So that was my last slide. I think I was on time. If you have any questions, I'd be happy to answer.